right, welcome to Miss Beardmore's Physical Science class's presentation on Chapter 4, The Laws of Motion. This is for people who have missed class or for students who just need to review the notes another time with my voice playing along with it. The first section that we're going to talk about is about the first two laws of motion. Okay, the first two laws of motion are referred to Newton's laws of motion. Isaac Newton, seen here, was a British scientist. He lived in the 1600s and in 1687 published 3 rules about motion. They were later named Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. Right, all about the first law of motion. Basically, what that says is that an object at rest stays at rest until acted on by an outside object, or an object in motion will stay in motion until an outside force acts upon it. Okay, so basically what that means in everyday terms is if the forces are balanced, the velocity of the object doesn't change. If they are balanced, then the velocity changes. Okay, so we have a picture here of a guy riding in a car, and in the first portion of the picture right here, we can just assume that he's riding down the highway at 60 miles an hour, and then all of a sudden in the second picture here, he slams on the brakes, and the car slows down, but his body is keep moving forward. Okay, so the forces changed on his body, the car started slowing down, but he was unchanged and kept moving. Eventually, the seatbelt right here, you can see, slowed him down and he didn't fly through the front windshield. Okay, same thing if we were going the opposite way. If you're sitting in a car at a red light and then it turns green and you stomp on the gas really quickly, you're going to feel like you're falling back into your seat a little bit more. You're getting pressed into your seat. Or if you've ever ridden a roller coaster, at the beginning of the roller coaster, if it shoots off really fast, you feel pushed back in your seat. If you're stopping really quickly, you feel pushed forward in your seat. Okay, it's important to remember that only unbalanced forces will change velocity. Think about riding a skateboard. If you just stand on the skateboard, both feet on the skateboard, you're not going to move, you're not going to do anything. So unlike this picture, having both feet on the skateboard means that the forces are balanced. There's no force pushing you forward, there's no force pushing you backward. The only forces that are working is the force pushing down on your body and the force of the skateboard pushing up on your foot. So nothing's happening. To make the skateboard move, you need to do like this picture. Have one foot on the skateboard and have another foot on the ground, like kind of pedaling or pushing to make you move forward. All right, and then you can put your feet on the skateboard and ride a little bit. Eventually friction takes over and slows you down, so you need to use a foot to push off again to build up more speed, use more force, get more acceleration. Same thing if you want to stop the skateboard suddenly. You're riding the skateboard and all of a sudden you want to stop, you take a foot off and step it down on the ground. That changes the forces, that unbalances the forces, so therefore you stop. All right, inertia and mass also have to do with Newton's first law. The word inertia you might not have heard before, but inertia is the tendency of an object to resist a change in its motion, and mass, as I'm sure you know, is how much material is contained within the object. If we look at these two pictures here, we have a picture of an 18-wheeler and we have a picture of a little beetle. Which one of these do you think has more inertia? Which one is going to resist a change in its motion more? Okay, hopefully you said the 18-wheeler, and we'll explain that in a second, but why do you think it's the 18-wheeler? it's the 18-wheeler, like we said about mass. It has more mass, so because of that, it's going to resist the change in its motion more than the tiny little car. So if you're driving down the highway, the Beetle and the 18-wheeler at 60 miles an hour, all of a sudden a deer runs in front of you. If you're driving the Beetle, you're going to stomp on your brakes and you're probably going to be able to stop in time. If you're driving the 18-wheeler, you're going to step on the brakes and probably not stop in time. It's going to take you a lot more time and energy to slow down because of more mass in the object. Or an example that you've probably seen more often, if you're sitting at a red light in a small car and somebody in a big truck is next to you, and when the light turns green, you both step on the gas at the same time, your car will probably accelerate faster than the big truck next to you because of inertia. All right, Newton's second law of motion. Let's go ahead and look at these pictures real quick. Which one of these guys do you think is throwing the ball harder? Okay, and what does the word harder really mean in this situation? Okay, hopefully, we said that the professional baseball player was throwing the ball harder. We would probably think that because he's older, he's a professional, he might have bigger muscles. The other little guy is just a little kid, probably just learning how to play baseball. So throwing harder, if we're looking at the professional baseball player, he's using more force to throw the ball. Force is going to be an important word here for Newton's second law of motion. Okay, another thing to think about before we talk about what the second law of motion really means. Think about rolling a bowling ball or rolling a baseball. Which of these requires you to use more force? Which one do you have to push on harder? Right, hopefully you said the bowling ball. And the reason why you probably said the bowling ball is because a bowling ball is bigger, it weighs more, it has more mass than a baseball. Okay? Force and mass are two important things for Newton's second law. Right, so what does the second law of motion actually say? It states that the acceleration of an object is in the same direction as the net force on the object, and that the acceleration can be calculated from the following equation. The equation is acceleration equals force divided by mass. If we were going to write that out in simpler terms, acceleration is represented by a little a, force is represented by a capital F, and mass is represented by a little m. So if we had an equation that we needed to figure out, we would use that. We would substitute some numbers in there to figure out anything that we need to be. Okay? All right, calculating force with the second law. Most of the time, we're not going to worry about calculating the acceleration. Generally, that's already given to us. Normally, what we want to focus on finding is the force required to get that acceleration. So the equation that we started out with on the last slide was acceleration equals force divided by mass, and we want to try to get force all by itself. So we're going to manipulate this equation just like you do in math class to try to get the x all by itself. This time we're trying to get f all by itself. Okay, so if we look at that equation, a equals f divided by m. If we want to take m away from that side, we're going to multiply both sides by m. And then after that, you just rearrange the equation. After you're finished with that first step, you have mass times acceleration equals force. Generally, we like to have one letter equals two letters. So our new equation is F equals ma. Force equals mass times acceleration. That's going to be an important one for us. All right, section 3 real quick is all about the third law of motion. All right, Newton's third law, what that deals with is action and reaction pairs. You've probably heard of this one before. For every action, there's an equal and opposite reaction. So like the first picture, the guy's pushing on the wall with 100 newtons of force. The wall's pushing back on him with 100 of newtons of force. So he's not moving the wall's not moving him. He's just pushing on the wall, nothing's happening. Right, in the second picture, if we have two guys on skateboards pushing on each other, they're going to push each other in opposite directions because of the equal and opposite reactions. Another way to look at that is that action and reaction don't cancel each other out. So the swimmer here, Michael Phelps, is swimming and his arms and legs are pushing on the water. The water's pushing back on him. So that's how he's moving himself through the water. He's not just sitting there doing nothing. He pushes on the water pushes back on him, which propels him through the water. Right, same thing happens in rocket propulsion here. So we have a rocket lifting off, going into outer space. Whenever it starts out, it pushes all of this hot gas out the back of the rocket. That's the action, the force on the gas around it. And the reaction is the force on the rocket upwards to push it up into outer space. Okay, and there's a little video recap here. I don't have time to show it to you in this little simulcast, but you can type in this YouTube link to watch a student-made video about Newton's laws.